trying to tangent. What I want to do today, and my hope is that this gets communicated effectively to you, is to explain not necessarily what are we doing, but more what is allowing us to do what we're doing. Okay? And if we can do that, if we can understand why our calculator is working the way that it is, because you're going to need a calculator for some of this stuff, whether it be Desmos or your handheld or whatever. If you do get Desmos, which is fine, if you get your computers out and have Desmos open, that's fine. I got on some people last period because they had their computer out claiming it's Desmos, but they're doing that kind of stuff, and that's not Desmos. What I want us to see and realize is when I type in on my calculator, sine of, let's say, 30 degrees, okay, why my calculator is spitting back 0.5. Or when I type in sine of 40 degrees, why that number goes from 0.5 to 0.64. Or when I go sine of 90 degrees, why it gives me 1 back, okay? So I want us to be able to know what that actually means, okay? Not so much, because I think in, the algebra standards are that you have hit sine, cosine, and tangent. You've talked about those things in an Algebra 1 course. Would you guys agree with that? Okay? So the idea is maybe in those courses you did something like, if this angle is 40 degrees and this is, let's say, h, but that's 5. You guys remember taking and setting up a ratio or a proportion to be able to solve for h? Okay. I want to talk about the geometry that allows this to happen. Okay. And then we'll have time eventually to actually talk about the process and the algebra that goes with it. But that's hopefully what I convey to you today. And it's going to start with looking at one of these. I just shut it down. Again, puberty. If I have a 30-degree angle here, and I want to use 30 degrees initially because of what we already understand about 30-degree, 60-degree, 90-degree triangles, right? We already have quite a good understanding. If I give you the segment from B to C, let's see, the segment from B to C as that distance right there, how are you going to find that distance? Or how are you going to use, that distance to come up with B to A if this is a 30, 60, 90 triangle? If this is, what side is what's across from 30 degrees in a 30, 60, 90? In your template. Using letters like maybe N and 2N and that stuff. Do we remember? It's N, okay? So then the hypotenuse is then 2N, right? Okay, so you can double this. And let's see if B times A, or not B times B 2A is double. So if I take that number and double it, it does give me that one, okay? And then this one here, A to C, would be that number times radical 3. And if you took your calculator, now there's going to be a little bit of rounding error because of what GeoGebra is using to get these values and what it's displaying, and how if you took 11.55 and multiplied it by, or 6.67 and multiplied by radical 3, you're going to get something in the ballpark of this, but you might not get exactly that, okay? It's because GeoGebra is actually not using 6.67. GeoGebra is actually using, to get the 11.55 number, GeoGebra is actually using more or less of that number. Does that make sense? And it's really not using that one. It's using, because that ends, right? What they're actually using is the irrational numbers that were used to find that distance, or that were generated when we found that distance. So if some of the things that we do today, if you're off by, a tenth or a hundredth or something like that, it's because of the number that you're seeing here being used by GeoGebra is actually a mitigating or eliminating rounding error, where in our calculator we involve it. Okay. What is happening here, if no matter what I do, if I take BC, okay, so I'm just going to type BC and I'm going to divide it by AB. Okay, so that is the opposite side of 30 divided by the hypotenuse. Okay, and that's going to give me that number right there you see is 0.5 being highlighted. Okay, no matter what I do, when I change the BC value and the BA value, okay, if I change those, am I still always getting a quotient that turns into 2.5, no matter what the numerator and denominator are? And it's because the fact of how this 30, 60, 90 degree triangle is structured based on that being n and that being 2n all the time. And we learned that through the use of the Pythagorean theorem. So the Pythagorean theorem is true, all this stuff is true. Okay? The argument is, okay, well, what can I call that ratio? What we call that ratio of opposite divided by hypotenuse is sine, right? Take your calculator out and type in sine, hit the sine key, S-I-N, and then hit 30 after it, and then hit enter. One thing we have to pay attention to is that our mode has to be in degrees, because that 30 is a degree. So I got to change that on mine. But if I type in sine of 30 now, I get that 0.5, right? So my calculator knows, hey, when we hit sine, we're talking about right triangle stuff. They're saying there's a 30-degree angle in this right triangle. Well, if I look at opposite divided by hypotenuse of a 30-degree angle in a right triangle, it's always going to give me a 1 to 2 ratio. So that's essentially a scale factor, but that's built in to our calculator. Okay? I can change that 30 to anything I want. I'm going to use Desmos to demonstrate this, because I can just change things a little bit easier on that. If I go sine of, I'm going to just say A here, and I'll make A go from, we're only going to be interested right now from 0 to 90. Okay? But if I do that, and I stop it, so sine of 17.5 is that number right there. Okay? The sine of 28.4 is that number right there. And you're going to get the same thing if you were typing in your calculator sine of 28.4. Okay? But it's telling me then that every triangle that has a 28.4 degree angle in it, and it's a right triangle, when you divide the opposite by the hypotenuse, you're always going to get 0.475 back. Okay? So in the last class, I kind of demonstrated that with this here. Okay? If I have, and actually I'll just cancel that out, do something different. Let's say we get a right triangle here. Let's go. Trying to find the best way of developing a right triangle. So I'm totally not worried when I'm doing this about size of segments or anything like that. All I'm worried about is that I get a right angle here. Okay. I'm going to put my triangle in here, and now I'm going to just make those lines disappear. And I want to ask this thing to give me the angles of this thing. Okay. So what I want you guys to do real quick is just type in on your calculator sine of, let's just get a number that's not close to anything that we've been dealing with, 30, 60, 90. So let's just, now again, I'm not worried about segment lengths here, right? I did not focus when I built this on segment lengths. So I want you guys to type in sine of 36.74957. And then just hit enter. Okay, so that gives you, wish my screens were a little bit bigger. All right, so sine 36.74957 gives you that ratio right there, correct? Take your calculator, because sine is opposite divided by hypotenuse, correct? I want you guys to take your calculator. I'm going to give you the opposite side of that 36 number, which would be AB. Type that number in. And I want you to divide it by AC, which is that number. So it's opposite divided by hypotenuse. When you do that, now understand, because of the rounding that is taking place here, okay, with these two distances being expressed from GeoGebra, and there's in the background, there's much more to those distances. Does that make sense? So they're much better if we go out 15 decimal places, but I don't want to kind of get too crazy with these. But if I go out that far, and I divide the opposite side of the 36-degree angle divided by the hypotenuse, is that number right there, up to 1, 2, 3, 4, 5 decimal places, is it the same as that one there? That makes sense? Okay. Now, what I'm going to do, just to prove this to you using GeoGebra so there's no rounding being involved, if I go sine of that angle, that symbol right there is gamma. Put that in there. So see what that gives me, and it gives me that number right there. I'm going to go out to 15 decimal places. Okay, so that's that number. Does that make sense, everybody? That should be identical to that value there divided by that one. Now, if I were to type that number in, because I'm not, here's the thing, we don't know if that's really a 5 right there where my cursor is, because we don't know the number to the right of it. Does that make sense? If I knew that number to the right of it, maybe that 5 is legitimately a 5, and the number to the right of it is less than 5. Okay? But the number to the right of this position could have actually been like a 6. And if it was a 6 and this was a 4, I would have rounded that up, right? So I don't know if this number should be a 5 or a 4. And that's really with anything that you ever see. I don't know if that's a 4 or a 3. Okay? When you're using your TI-83s or TI-30s or whatever they are, okay, when I type in, say, for instance, sine of 33 degrees, I don't know if that's a 5 or a 4 right there where my cursor is. Okay, just the way rounding works with technology. So I'm not going to use this. I'm not going to type that number in. I'm going to take AB. So when I type in AB, GeoGebra is going to capture this entire decimal for thousands and thousands of decimal places. Does that make sense? And then we'll divide by AC, which is going to do the same thing then. Okay? And when I hit enter, I look at those two. I look at D, because D was the sine of that 36.749 angle, right? This is the quotient of the opposite side of the hypotenuse. Okay? Now, if I look at, I'm just going to go D minus E real quick, and to show you that D minus E gave me 0. So what's that tell me that D and E were? If their difference is 0, that means they're the same number, right? So hopefully that's an argument to show you that the sine of that angle is identical always to what the opposite distance divided by the hypotenuse distance is for that right triangle that incorporates that right angle. Or I guess that 36-degree angle in this case. And that's going to be the case no matter what. Change this angle. So now I've got a, can't see it, 51.66 degree angle. Okay? This would be the sine of 51.66 where my cursor is. Okay? This here would be the 5.4 number divided by the 6.89 number, and it still gives me the same thing. So our calculators are programmed to know that. Okay? Now, I'm not going to get into the detail of that programming. It actually uses a function. It's called I believe it's a Taylor series or a Maclaurin series from calculus that actually uses an estimation process for us. But what I want you guys to realize is when our calculator gives us sine of 33 like this, okay, that's really not the number that we're really using. Sine of 33. Now with this program to show you this calculator what sine of 33 really is, I can't use degrees, so I have to use what's called radians. So I'm going to say A is equal to, so 33 degrees, if I multiply that by pi divided by 180, that will give me what we call radians. So that, you remember talking the other day about like kilometers and miles? Like we don't necessarily understand kilometers that well because we don't use them very often, but we know miles are, right? So this here is a radian. It's the exact same angle measurement as 33 degrees. I think you guys would probably be more comfortable if I say, draw me an angle of 33 degrees, or approximate an angle of 33 degrees, versus approximate angle that's 11 pi over 60 radians. And that'd be hard for us to draw, right? Or to visualize. But they're the same thing, just different measurements, different units or labels. So now I'm going to ask this thing to evaluate the sine of that angle for 10 decimal places. So this is what your, that's going to be a comma. So this is what your calculator would give you back, 0.544. If I go sine of 33, is that the same one we get back? Okay. Now if I go to 11 decimal places, just to kind of talk about that situation earlier based on my calculator, now I know that actually was a 5 right there on my calculator, because if I look at this number, it's a 0 right after it, right? So the rounding of the calculator would have told it to stay at 5. But I think 100,000 is my limit. I don't know if I showed you guys this with pi at one point. Okay, that is actually the number sine of 33. Okay, and that is only 100,000 decimal places. So that, in actuality, is a very, 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 very poor rounding of sine of 33. Because if that's an irrational number, there's no repetition, there's no repeats here. And if I have 100,000, we talk about irrational numbers, they go on for how long? Forever, right? Okay. So 100,000 is pretty small in comparison to forever. Okay. So that is, even though it's a lot better than, the 10 decimal places that the TI-83 gives us, it's still bad in regards to accuracy. Okay. Now there will be times when we're working with these numbers that, this is fine. For everything we do, this will be fine. For everything that you do in high school, this will most likely be fine. Okay. But if I'm working for NASA and I'm trying to use this stuff to determine orbits and that kind of thing of satellites, that's not fine. That's a problem. Okay. If I'm using this stuff, let's say I'm building something at home and I need to go to Lowe's and I need to get some lumber, I'm not going to go there with sine of 33 on my mind. Does that make sense? Eventually we're going to, and I'll explain this in a little bit, we'll have we're going to use this as a scale factor to multiply by some length. I'm not going to go to Lowe's and say I need 17 sine of 33 feet of lumber, right? Does that make sense? I'm going to type in my calculator, get a decimal, and say, hey, I need 15 feet of lumber. I'm going to round up pretty bad. So those are little things that we need to understand. There's context to problems. When is it important to round? When is it unimportant to round? Does this kind of make sense? What we're trying to get at here, what this stuff, what these relationships are? I think you've been shown how to do it, okay? But I don't know if we've been shown why we do it that way, okay? And why that works. Remember back to, let's see here. Let me just draw a quick picture here, and then we'll get into actually using these ratios. I want to tell you that these two triangles are similar, and I'm going to tell you that we'll just call this A, B, C, and A prime, B prime, C prime. Let's say this is 5 and this is 2. If I give you this to be X, okay, and let's say this one here is 7, and I told you the two triangles are similar, do you guys remember saying that 5 compared to 2 is equal to X compared to 7? Remember doing that? Okay. Well, this is the opposite side. This is the adjacent side if I'm looking at angle C. This is opposite, and this is adjacent if I'm looking at C prime. Okay. What this allows us to do, if you know that angle, let's say that angle is 28 degrees, what's going to happen is that you're not going to know that. You're not going to know that 7, you're not going to know that 2. And if I don't know that 7 and I don't know that 2, then I don't know the 5/2 ratio. Does that make sense? Okay. However, so I'm not going to know that, but if they both have a 28-degree angle in them, I know that that side divided by that side and that triangle is identical to that side divided by that side. So tangent would be the ratio I use here. Tangent of 28 takes the place of that 5/2 ratio. Does that make sense? Okay. And we go through and we try to solve effects, and that's really the exact same thing we did in 7.2 and 7.3 and 7.4, except for now they're giving us less information. We don't know both triangles. Okay. We know that this one here is similar to that one, and any triangle has a 28-degree angle and a right angle. That ratio is going to be consistent all the time. So let's get into actually using this. And I think, guys, if you don't understand what we just did, you're still going to be successful to an extent with this stuff. But the more you understand what we just did, the easier the stuff is, less confusing it is, and you'll breeze through it, and you'll know when to use it, when you can't use it, what it means to you, and how to actually manipulate the algebra that is involved. All right. The first handful of questions that they're going to ask you, they're going to give you all 3 segments. They're going to give you one triangle, they're going to give you all 3 segments, and they're going to say, look at this angle T, look at that angle T, and just write what the sine, the cosine, and the tangent are for that angle. Okay? The structure of the way of using these things, that thing that's in the parentheses, we call it the argument, is always your angle. Okay? So you're always going to put parentheses, and then the angle that you're focused on or interested in the parentheses. So once I look at angle T, I'm going to go through and I'm going to label these sides. What would 8 be? Is that the opposite, adjacent, or hypotenuse? Okay, angle T, is that opposite, adjacent, or hypotenuse? It's going to be opposite. Okay. Remember opposite. So opposite, and this is common. Opposite is if I were to, I kind of used the idea that this was a yellow angle was a flashlight the other day. It's going to shine on that wall over there. Does that kind of make sense? So it always shines on the opposite wall or the opposite segment. If that's opposite, then this one here is adjacent. Okay. So a couple ways of thinking about it. You can think about opposite and find that first and know that's got to go across the interior, or adjacent meaning that it's right next to it. You agree that this one compared to the 8, that 15 is right next to T rather than 8 right next to T? So we get sine. So sine, okay, sine is opposite over hypotenuse, okay? So that's opposite, that's adjacent, this is hypotenuse. So if I go 8 over, so remember this is opposite over hypotenuse, so it's 8 over 17, correct? That's the only thing that they're asking you to do here with this particular question, all right? And what they're saying, and I'll show you, demonstrate this in a minute, that no matter what this yellow angle is, no matter what that yellow angle is, okay, in every other triangle that has that same yellow angle, when you divide the opposite divided by the hypotenuse, it's always going to be an 8 over 17 value, okay? And we'll talk about that in a moment with the decimals. Take a minute knowing that cosine and tangent from SOHCAHTOA. See what you get with cosine and tangent. Okay. It was, all right, so cosine adjacent divided by hypotenuse, right? Okay. So the adjacent side, we labeled that as 15. Hypotenuse is 17. And then tangent is opposite over adjacent. So that's the TOA, right? So that's 8 over 15. Okay. Now, and we'll learn this in a couple days, but I'm going to use GeoGebra to figure out what that yellow angle actually is. Okay, so I'll go arc sine of 8/17. So that yellow angle is actually 28.07 degrees. Okay, so every triangle that has that in it, if I look at 8/17 as a decimal, is going to give me that decimal when I compare the opposite side of the hypotenuse. So I'm going to draw a right triangle here, and as I'm drawing this, understand that I don't care what my lengths are, okay? So I've got that there. I need that angle of 28.07. So I'm going to get GeoGebra to just copy that angle, and it goes through B prime. All right, so that's one of my angles for my right triangle, correct? Now, I don't care how long my sides are. So I'm going to go perpendicular line from there to there. I just need a right triangle, correct? So if that is a right triangle, I'm going to, I need that intersection point. Get rid of that stuff. So got this right triangle. Don't really care how big it is, and just messing around with, obviously, don't care about size, okay? But it does have that angle. If I take the opposite side, which is going to be that distance right there, and divide it by that distance right there, okay? Let's see what that gives us. So I go B prime divided by C, or sorry, so B prime to C, divide that by B prime to A. So that's, that numerator is the opposite side of this angle. That is the hypotenuse. Hit enter. What do you recognize about these two numbers? They're the same. Okay? That one there was 8/17, right? This one here is the quotient of the opposite side divided by the hypotenuse. It's not, this side was obviously not 8, right? This is not 17, okay? But we know, much like 2 divided by 4, same thing as 3 divided by 6, same thing as 6 divided by 12, right? Those are equivalent quotients. This is an equivalent quotient to 8/17. And as I move things around, okay, move this triangle down to that size. Now I'm taking, right here, I'm taking 5.3 divided by 11.3, but you still see you get that exact same sine of 28.07. Okay? So that, my hope is, demonstrates that we're not This stuff's not like magical. It's not, and I think that's what a lot of people eventually start to think about these is, okay, I get the process, but it's just spitting out a number. How can I guarantee, how can I be convinced that that number is what it is? We're going to go through a process here and find W, and hopefully what we just talked about convinces you that that is 100% an accurate result for W. Okay? So with a question like this, they're going to give you just this information. Okay? We're going to focus on the angle that they give us. And we'll talk about this here in a moment, about maybe some options. But that is the angle that they give us. They ask us to find W. Okay? So in my equation, when I'm generating my equation, I know I have to use W. Does that make sense? Then that is the only variable, that's the only unknown. Everything else, there should be two other things. Two other things need to be known. An angle and one other side length. Okay? And we've got that. Okay? So what I do is I go through, I look at my angle that they provide me, and I start labeling the sides in regards to what that angle is. So what would the side over here, W, be called? Is that the adjacent, the opposite, or the hypotenuse? That's the opposite. Okay? And what's 17? The hypotenuse, correct? Now, I'm not asking, not at the moment, but this then would be the adjacent, correct? Like I said, we've got to use the 54. We've got to use W. And we got to use hypotenuse. So the trig ratio that uses the opposite side and the hypotenuse is the sine ratio. All right, sine. And then what goes in here is the angle that determined what was opposite, what was hypotenuse, and what was adjacent. So sine of 54. And then remember, sine was opposite divided by hypotenuse, right? So the opposite in this case would have been W. In this case, this is 17. Okay? So that sine of 54, guys, that is like in 7-2, when we were able to look at two triangles and say, oh, this one has a maybe a hypotenuse of 12, and this one has a hypotenuse of 15. Well, the scale factor would be 12 to 15. This is saying what the scale factor is. Okay? And if we want to think about it this way, if I go sine of 54, it's saying my scale factor is 0.809 to 1. Does that make sense? So one of my triangles has maybe a length of 1. The other triangle is 80% of that. Okay? That's one way to kind of think of and view that. But algebraically, this is like a radical almost. Okay? It's a symbol for another number, right? That is a symbol for that 0.80 number. We're going to leave it that way because it's an irrational number. How do I get this W by itself? That's what I'm trying to solve for, right? When you have fractions in your equation, what do you always want to multiply by so that fraction goes away? You guys heard of least common denominators before? LCDs? I want to multiply by an LCD. And that LCD is 17, right? You can even cross, it's a proportion. If you want to cross multiply, you can. I'm going to get 17 times sine of 54 is equal to W. Okay? That's the exact answer. And this is what I was saying earlier. I'm not going to go to Lowe's and tell them, hey, I need 17 sine 54 feet of lumber. I'm going to grab my calculator. And we'll type in 17 sine of 54. And I get that number right there. Okay? What I want you guys to see and realize here, so that is W, that's that opposite side. If I'm not paying attention to whether I'm in radians or degrees, I might get that number. That's completely different, right? It's still 17 sine of 54, but 54 radians is an angle that is much, 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 much bigger than 54 degrees. Okay, much like miles and kilometers are different sizes, right? So I need to make sure I'm in degree. So that's 13.753. Is that okay with everybody? All right. Let's make a comparison, and this hopefully makes use of cosine real quick. Let's go. Just do this real quick for me. Take your calculator out. Type in sine of 54 degrees and tell me what number you get. 8090? Okay. And that's an approximation, right? Let's go cosine of 36 degrees. What's cosine of 36 degrees give you? Same number, right? 0.8090. So here's my question. Those two numbers are identical, right? What's that tell you then about those two numbers? They're the same. Sine of 54 is the same thing as a cosine of 36. What's the relationship between an angle of 54 degrees and an angle of 36 degrees? They're what to one another? What do they add up to? 90. So they are, two angles of F90 are complementary, right? First two letters complementary. CO, right there. Okay? So the names of these, sine and cosine, should help us realize that if I want to use sine of 54, I can use sine of 54, and I can get the answer, but I can also use this angle here, which is 36. But now what would I use in 36? What would this side here be labeled as? What would W be if I'm focusing on 36? Won't 36 be the adjacent side? 17 be the hypotenuse? So now if I say cosine of 36 is equal to W over 17, I'll get 17 cosine 36 equals W. And what we just said was that sine of 54 and cosine of 36, that there and that there are the same, right? We multiply them both by 17. So if you type in 17 cosine of 36 or 17 sine of 54, they should both give you that 13 number that we got. Does that make sense, everyone? All right. Let's go. You guys take a moment. See what you can come up with here. If I give you that 54, focus on the 54. You're going to have to relabel your sides here, but I want you to find X. Okay? Just a new problem. Don't even worry about W. Find X. You guys end up with 17 cosine 54 as the algebra before we type in our calculator? Okay. So that turns out to be 17 cosine of 54 gives me 9.99. Okay. So W was that number there, right? X, I said, was that number. And just because of the way Desmos works, I don't want to use X. I'll call it A. What kind of triangle is this? It's a right triangle. So what number one theorem works with right triangles? Pythagorean theorem. I take this 13.75 number, which this is an irrational number, and I'm going to square it. I'm going to add to it this number here, which is that adjacent side x. And I'm going to square that. It's kind of weird, but I get that number right there. Took two irrational numbers, squared them, add them together, I get 289. How does that 289 relate to 17? 17 squared. 289, right? So what did we just demonstrate was the check to see if we did this stuff right. What theorem is this? Pythagorean theorem, right? So when you go through and you find distances of your triangles using whatever approach, special right triangle, SOHCAHTOA, whatever, you can use it. Once you have all three side lengths, you can use the Pythagorean theorem to check to see if you've done everything right. Okay. My hope is that through today's discussion we understand a little bit. I'm not saying we've mastered it and we're going to get it every single time when we start talking about it, but you get a little bit of an understanding that there is logical, foundational ideas behind the sine of 54 giving me this decimal back, okay? Why the sine of 30 is 1/2 and that sort of thing, okay? Told the last class, if you're working with special right triangles, the benefit of special right triangles is that we get an exact answer, okay? If I know, for instance, like this is, let's say if this is 30 degrees, and this is, let's say if the hypotenuse is 8, actually let's make this 60 degrees, make it easier. Oh. If this is 60 degrees, then I know automatically this is 4 radical 3. Does that make sense? Okay. If I didn't use special right triangles, I could say, I'm looking for this here, I'm looking for that x. I could say sine of 60 is equal to x over 8, opposite over hypotenuse, right? And we'll type in what that number is. If I type in 8 times sine of 60 degrees, sure, I'm in degrees, I get that distance right there. Does that make sense? Well, that distance right there is 4 times the square root of 3. Okay? The benefit of a 30, 60, 90, though, that's exact. 4 radical 3 is exact. And this is obviously a rounded decimal, right? Okay? Understanding that idea is that my calculator does not have the ability to go from a decimal to the exact. So in your homework at any time, or the end of course exam, or tests, or whatever, if it says, look at this right triangle and find the exact answer, that's indication that you should not be using sine, cosine, and tangent. You should be using special right triangles. Because sine, cosine, and tangent rarely are going to give you exact answers. Okay? They're going to have to be rounded. Does that make sense? The only time they're going to give you exact answers is if the angles that you were working with were 45, 30, or 60. All right? So just kind of keep that in mind. I put on 8.3. Whether we're going to be here or not tomorrow, I don't know. So it's going to be due Friday. Okay, so give you all day tomorrow if we're not here. We're going to keep working on this stuff. And like I said, I mentioned this a couple days ago. Chapter 11 and 10 are about area, surface area, volume, densities, masses, that kind of stuff. Those are formulas, very heavily laced with formulas. And instead of like in like 7th grade where, let's say that the volume of a cone is 1/3 pi r h, or pi r cubed h, pi r squared h, sorry. Instead of just giving you r and h, you're going to have to work with special right triangles and sine, cosine, tangent to find r and h. Hey, you too.